So I chose this paper today for a number of reasons. One, Sebastian Thrun is one of my favorite paper authors. He's he's one of the grandfathers of like modern machine learning. And what I like is that a lot of his papers are about new problem formulations. Like the other paper that I've read of his in a lot of detail is the one describing partially observable Markov decision processes, which are like one of the standing jokes if you do decision-making research in machine learning is that like every single problem can be formulated as a partially observable Markov decision process. It's like one of those really nerdy jokes. But it's just because the idea behind it is that we can only observe the world and we don't know its true state. And so when you're trying to make decisions, you have to make decisions with partial information, and that's why it's called partially observable. But anyway, this is another paper he wrote 27 years ago, and it's about lifelong learning, which now in machine learning is called continual learning. And it's the idea that throughout like an agent's life, where an agent can be like a computer or it can be a person, you have to learn to do more than one task. And a lot of these tasks have shared characteristics between them. And how can we leverage our experience from past tasks in order to make ourselves more effective at learning how to do new ones? And so that's why the paper is called, "Is learning the nth thing any easier than learning the first?" Because it's about, can we make it easier to learn the 10th thing we learn versus the first thing that we have to learn? And one of the things that the author cites as like an inspiration for this paper is it's shown that people use like, first of all, they're able to generalize really well with very little data. Like I think the example I've heard of this before is you see a zebra once and you could probably recognize it for the rest of your life. Whereas if you had one picture of a zebra for like a computer and then you wanted it to recognize a zebra versus like a horse, it could be very, very difficult / impossible because the really effective models we use are very data hungry. So people are really good at generalizing with sparse data, and we have a lot of psychological experiments and studies that show that this is because people use what they've learned from tasks, and they transfer knowledge from other tasks in order to be better at like the new tasks that they're trying to learn. And so for this paper, we'll just go through it, but basically it's we'll just go through it because I'll introduce the experiments later. So the key idea is to transfer knowledge across multiple learning tasks. And one thing to recognize from that, like on a very broad level, is that this this approach is only useful when there is shared characteristics between tasks. So for example, if you were trying to use like images to teach a computer how to recognize words that are based on audio files, that's probably not going to be useful. You never know. Maybe there's some like kind of connectivity in the brain that we don't know about, that where those two types of information can be represented in a similar format. Anyway, so in the introduction over here, what they're doing is just laying out the framework, which is, and the idea behind supervised learning, which is that, so you have some data set of input features called X, and then you have some function F, which is like, X could be an image, F could be a mapping to whether that image is a cat or a dog. And then what you do is you assume that F comes from some class of functions, and you create a hypothesis space for that. And like, for example, the one that we use a lot today in deep learning is we say, okay, we have a neural network that has 5 layers with weights that are real numbers in each layer's matrices. And the hypothesis space of the function is like all the values that these weights can take. And so you're saying that your strong assumption, which is the assumption of the model, is that the mapping that you're trying to learn, F, is actually can be described by like a 5-layer neural network with some, if you were able to find the right numbers for the weight matrices. Yeah. So that's the supervised learning context that they're saying is like the canonical way that we do machine learning now. But then the lifelong learning one is, instead of trying to learn a single function f, you're trying to learn a group. You over time you learn f1, so that's your first supervised learning task, and then you have f2, your second, and your third, and so on. And for this paper, they look at what they call the most simple form of lifelong learning, which is concept learning. And the reason why it's simple is because you can say something is a concept or it's not. Like, this is a can or it's not a can. This is a person or it's not a person. And these are abstract concepts because you can't observe them directly. Like, there's no like person, there's no what's it called? Measurement tool which tells you this is a person. You know, there's just, we get an image and we have something that processes it and outputs this is a person. So anyway, so the problem that they're trying to solve is you have n functions, f1, f2, f3, and for each of them you have its own data set. So xk, there's x1, x2, x3, and you're given a new data set and you want to learn a new concept. And that's the problem formulation of this paper. And what were some things that I wanted to point out? Oh, one thing that I wanted to point out is that the author states over here that one of the main benefits of lifelong learning or taking this approach is that you can learn something with very little data about it. So you could, like we talked about before, you could get one image of a zebra and be able to accurately classify with some computer model, this is a zebra when you see new ones, instead of needing like millions of images. And the other cool thing is this term, which is saying that there's synergy between the different tasks, like learning F1, learning F2, learning F3, which means there has to be some shared structure between them. And okay, let's see over here. Okay, and so for this problem, the previous F1, F2, F3, up to Fn minus 1, where n is the nth concept you're trying to learn, is called the support set. So you have n data sets that you want to use in order to learn Fn. And a point they make here is that the support set usually cannot be used directly as training patterns with learning a new concept, since they describe different concepts. So basically it's saying we can't actually reuse the examples. Like, so say we're trying to learn some model Fn, and we have all these past data sets of images of objects. We can't reuse those examples in our new data set because we actually don't know how they're related to it. So we can't say like this. I think a good example is like, say you have a data set of plants and you have a data set of trees and animals. Well, no. How do I put it? Basically, you don't know how to relabel the past data sets for your current data set because you don't know the relationship between concepts, and consequently, you can't directly use x1, 2, 3 for xn. Let's see, what's a good example of that? If anyone comes up with an example while I'm trying to think of one, let me know.
You can think of the MNIST data set, and you're learning to classify numbers. Then you have the omniglot data set, which is random symbols. So you wouldn't be able to say that's not a 1 or a 2 or a 3 or a 4.
Yeah.
But you're able to say that's not a number.
Yeah.
So that's the concept.
Well, that's an example of where you can actually create a relationship between concepts. But I think that's because we have some domain knowledge which allows us to do that. But say you were trying to apply this problem formulation to a computer, like how is a computer without some more domain knowledge going to know that like these random symbols are not numbers? So anyway, that's the point that they're trying to make, that you can't directly use these past data sets in order to train a new model. You have to find some special way of incorporating that. So that's one concept that they point out. The other one is this idea of invariances. So when you're trying to learn concepts, the goal or the hope is that there's shared structure in how you learn these different concepts. Like the example that they give from images is that it doesn't matter if you like rotate an image or if you translate an image. If there's a face in it, that face will be a specific person's face. Like Rich's face will always be Rich's face, even if you rotate the image or translate it. So that's an example of how there's invariances within domains, means things that you can change, but it doesn't change the concept. Basically the idea is that you want to find a way to learn these invariances from the previous data so that you can ignore them and look at only the salient information that's required, like the important information for learning that newest concept. And so they, so of course, this is a research paper, and so there's a baseline for it, and then the new idea. And the new idea is leveraging these past data sets. And the baseline is like, okay, you only have that last data set, and you're trying to learn those last models. So you're trying to learn, like you get a data set of cats and not cats, and you're trying to learn from that data set cats, whereas you have a data set of a lot of different animals, like you have n data sets of animals, and you're trying to leverage those. So they say there's two approaches, which are memory-based approaches and neural network algorithms. And here I like that this is so old, because it's like, this is a really fundamental idea in machine learning, which is that you can either have a method for classifying something or mapping something, which takes into account the data points in your training set at test time, or you can learn a model which learns rules from the training set in order to classify it. So like the memory-based approach is like you are looking at your training set at test time. So when you're trying to classify cats, and the neural network approach is you only look at your data set at training time, and then at test time you feed your new example through your model. So first they talk about memory-based learning approaches, and they look at two. One is the really common nearest neighbor. So for the nearest neighbor algorithm, so you have your training set for your, let's say so the task we're trying to learn for the sake of discussion is to classify cats versus not cats. It's like the classic one in computer vision. So the way it would work is you have your data set of cats versus not cats. With nearest neighbor, you would get a new image, and you'd find the 100 nearest neighbors, and you would average their labels from the training set of cats versus not cats. So you might, and if the average is over 0.5 because your labels are 0 or 1, then it's a cat, and if it's less than 0.5, then it's not a cat. So that's the nearest neighbor memory method. And then there's Shepard's method, and for Shepard's method, instead of looking at like 100 points, you look at the entire data set, and you weight each point in your training set based on how far away it is in distance from your query's image. So basically you would do something like, you would take two images and take the difference between their pixel values, and then get the some mean squared error, and that would be your distance, and you weight each image accordingly. So these two approaches, they say like they exclusively use like the cat not cat data set, and so there's no obvious way to incorporate those previous sets into it. And then the author suggests two ways in which you can incorporate previous data from different problems into the problem. So the first one is representation learning, which is, and the second one is learning a distance function. And before I introduce those two ideas, one thing I think is really interesting is that they're very interesting problems, both like approaches, both of them, but representation learning seems to have taken so much more of a hold on modern machine learning than distance function learning. So I just thought that was really interesting that, like, you know, this is 27 years old and this is the paradigm we use more now. But anyway, so the idea behind representation learning is that you learn some model, like in this case, it's a neural network trained using backpropagation. And what it does is it takes your input set, so your input set could be images, and makes it into a smaller representation. Like a 32 by 32 image of pixels is 32 times 32 times 3 numbers. And maybe it will make it into like a 64 dimensional vector, so 64 numbers. And so it goes from the large representation to a smaller one. And the goal is that you learn in your support sets, using your support sets, mapping where the distance between, like, say one of our support sets is dog, not dog. You want the examples of dogs to be close to each other, and the example of dog and not dog to be far away from each other. So that's what this training objective is saying, that I want you to map the this new number space where dogs are close to each other and not dogs are close to each other. And then you do that for every single training set. And the idea there is that you learn to capture invariances. That's why you would use representation learning, because the goal is that you throw away useless information from the image. Like one common thing in computer vision is that, objects are usually in the middle of a camera image. So in a lot of computer vision tasks, like you can just completely ignore the boundary pixels. But, and that's something that you could learn with this type of mapping. So representation learning, that's what it's doing. It's trying to throw away useless information and only concentrate on the things in the picture that are, and encode that information in numbers that can be used for classifying things. Like maybe if you're trying to distinguish between like cat and not cat, it might be like, does the thing have whiskers, or does the thing have pointy ears? And if you were looking at multiple animals, it might be like, can I recognize legs or eyes and stuff like that? And one thing I just wanted to point out is that the G, which is that model that learns the new representation, it's trained, it's a neural network trained using backpropagation, which means that it's looking at the entire data set each time it does an update, which is just not something we do now. So it shows you like back in the day, they used to use backpropagation. But anyway, so the idea is you learn this representation, and then you can use a standard memory-based approach like nearest neighbor on top of it. But there's transfer learning there because the representation should allow you to generalize better, because it throws away useless information, and you learn how to throw away useless information using your support sets. So those previous sets. Yeah.
So just you then use these nearest neighbors or shepherds method on the representation space instead.
Yeah, yeah. Okay. Yeah. So what you would do is you learn this model, you'd get your new data set, or you would get your new point, which you're trying to say, is this a cat or not a cat? And you would look at your data set of cats, but you would, instead of looking at the images, you would look at the vectors that come out of G, the model, and you would do nearest neighbor on those.
Okay.
And then, so the second idea, which is one I really like, it's called learning a distance function. And I like it because I can't decide whether it's meta learning or unsupervised learning. But to me, it kind of feels like a meta learning method. And it's cool because meta learning didn't become popular until like 3 years ago. But this feels like a meta learning method to me. And so the idea behind the distance function is really, really simple. It's that you have your distance function takes in one image and then another image, and it outputs whether they're the same concept. So it's going to say like, you get an image of 2 cats, and it should say this is a cat. These both are the same thing. Or you get an image of a dog and a cat, and it said these things are different. And I think the really cool thing about this is the task itself generalizes across concept learning, because you could, if you have an example of a concept, like just one example, and you want to figure out whether something else is the same concept, like if they're both cats, you can use this function, because that's its whole goal, just saying these 2 things are the same or different. And so the way it works is the training objective is just cross entropy loss, where you're saying like, when concepts are the same because you have data sets where you have positive and negative examples of them. So for example, what you would do is you would take your cat data set and you would group pairs, which are cat and not cat and cat and cat. And those would be your training examples, because you have examples of cat and cat, which are the same, and cat and not cat, which are different. And you could do that for all of your previous data sets as well. So you can have like dog and not dog. And you train your model D, which is again like a neural network trained with back propagation. And then at test time, what you would do is you would just, what they say here is you take all the positive examples from your data set. So you take all the examples of cats from your final data set, and you feed them into the distance function as one input, and then you feed in the other input, which is your query point, which is the thing you want to know whether it's a cat or not a cat. And then you use Bayes' rule in this formula over here in order to figure out what's the probability that this is actually a cat. But anyway, the key cool part is the idea that all the thing is doing is saying whether this is the same and this is different. And I've come across this before as a problem formulation. And I think it's really interesting because, with computers, there's this one of the fundamentals of computers is that you can reduce any operation into like 3 or 4 operations that computers perform on their CPUs. I don't remember, it's like read, write, something like that. With intelligence, like I think a fundamental question that we try to answer in machine learning is like, can you do the same thing with machine learning and the way we think intelligently? And possibly, I think that like the idea of just having something, like what if we had in our brain something which could perfectly classify, this is the same as this, or this isn't the same. And then you could probably extrapolate that to come up with much more complex decisions. What I'm trying to say is like, it's as an idea, it's like it could be like one of the fundamental ideas for creating intelligence from really simple tools. So anyway, that's the, I want to just check if there's any question. Yeah.
I wanted to ask, because you said that representation learning has taken a hold of machine learning more distance function, but I don't think that's necessarily true. It's just not called distance functions anymore.
Mm-hmm.
But this idea of putting 2 examples on a target and compare the examples, it's used a lot. It's just not called a distance function. Like,
but what would you call it? Oh, BERT.
Well, in BERT, for example, one of the targets is next sentence prediction, which is a distance function. So you have your 2 sentences.
Yeah.
0 or 1. It's also like the Q&A matching.
Yeah, yeah.
What is the answer to the question?
Yeah, that's fair.
I think people just did away with the abstraction that you're learning a distance function and just call it something else.
But the reason why I say that is like there's an entire conference related to representation learning, whereas this is like a method that's spread out throughout. But you're right, actually. That's just like my subjective opinion of it. Yeah, they just, over here, they're pointing out that this generalizes the idea of a distance function. It's not actually a distance function because it doesn't meet the criteria of a metric. And then they just talk about, then they talk about their other baseline here, which is using neural networks, backpropagation. Okay. Sorry, I just have to read this. Oh, okay. So they have they have 2 methods that they use for as neural network approaches. One method is called learning with hints, and the idea is that you train a single model with multiple outputs to classify all of the different things. So the way you could think of it is, say we had two data sets. One was for dogs and one was for cats. Is that you would have 2 numbers outputted. One would say whether it's a dog and one would say whether it's a cat. And by having that like encoded into the network, the idea is that the internal representation will learn the invariances for all of the functions. So it's like a way of incorporating the support set. That's what's called learning with hints. And then they have this thing called an explanation-based neural network, which I didn't look that much into. but it supposedly it takes into account gradients, and in some way can use the support set. I'm not going to go that much into it because I basically didn't have enough time to understand it. But it uses gradients as an extra amount of information to figure out whether something is a cat or not a cat. Maybe we'll go back to this after I'm done and talk about like how you could use gradients, because I'm not exactly clear on how you could, if anyone has any ideas. Okay.
Yeah. So what I'm seeing is that like it's quite restrictive on the kinds of problems that you can use as your F1 to F(n)-1.
Mhm.
They're basically like it's talking about binary classification for things that are exactly the same shape. Like this.
Yeah, so that's very true. The author intentionally uses a really, really simple example, and that's because this is the first time that this idea has been introduced. But it is very limiting, because basically everything, all the tasks that if you want this to be useful, all the tasks that you're performing using this method on have to be similar.
This learning with kids, so how is it different just from multi-class?
No, it is. Well, yeah, it's basically a multi-classification problem, but it's not multi-classification like in classifying ImageNet, where you have like 1,000 different classes. Where there you're weighting each one against each other. So we'll take the really simple example of cat and dog. It's like you have a cat, you're trying to classify whether it's a cat or a dog. That's like multi-classification. Here, you would actually, and consequently what you do is you're weighting one option versus the other. Here, you're saying each option is independent. So mathematically, you would use a sigmoid function at the end instead of a softmax function. And then you would just be, and what you would do is when you're training it, if you get an example of a cat versus a not cat, you would only propagate information through that output, as opposed to all the outputs of the model. And if you get a dog, then it would be only through that output. So it's different because you're not saying this is the out. For multi-classification, you're weighing your options between the options. For this example, for this problem, you are only looking at a single option in each case. And so consequently, what could happen is with a test point, you could say like, this is a dog and this is a cat. Like you could get a probability greater than 0.5 for each of them.
But if we go back to this introduction, let's say you look at the zebra for the first time. In this case, you have to look at everything at the same time.
Well, so one of the ideas of the task, you know which task, you're not trying to classify between all of the past animals in this setting. You're just trying to classify the newest one. So it's the problem formulation that means that you would know you're trying to say cat versus not cat when you get a picture of a zebra, because that's the task that the nth task you're learning. Yeah. So yeah, now they do experimental results, and they use a computer vision task. And the task is you have images of, where are the objects? Oh yeah. So your training set is pictures of bottles, hats, hammers, a Coke can, and a book. And then the task is that you're trying to figure out whether something's a shoe or not a shoe, but you're given examples of shoes and sunglasses. So it's an example where like the images that you're comparing against, you haven't seen them. And the author says, since these, like he talks about how for computer vision tasks, like if you rotate the image, you translate the image, scale it, change the lighting, all these things don't change like the object that you see within it. And consequently, there's these invariances that you can take advantage in this lifelong learning context, because maybe by having more data and using these methods, what you can do is you can learn to ignore when an image is rotated and you're trying to figure out whether it's like a hat or a cat or a Coke can or whatever. And so like here's like the first set of results, and what they do is, so you have these two memory-based approaches that don't use transfer learning, lifelong learning, and then you have representation learning plus Shepard's method, and then you have the distance function method, and it's showing that they outperform here. They outperform the memory-based methods. And then you have backprop, which is it's just a neural network that looks at the most current data set. So this is like, again, like these ones, you only see the most current data set. You don't see the previous ones. And it's worse than if you did the one with hints, but not that much worse. Or it's also like this explanation-based neural network does better. So maybe it would have been worth learning those, what that was. But the key idea for this experiment is you only get a single example of the new object. So it's like one-shot learning here.
And then you're testing it on the rest of the data set.
Yeah. Yeah. And so the point is, if you look at the next results, one thing I wanted to just point out is like, so all of the tasks that you're doing are binary classification. And so the author says, notice that random guessing classifies 50% of testing examples correctly, because if you guess 50% of the time, you're right. And I wanted to point that out because I think it's one of the things when you're making models that you forget in classification. And then you might get it, you're like, well, I improved my model from 20% to 30% in binary classification, but like just random guessing would have done better than anything. So it's just one of those things that it's good to take into account.
So
yeah.
So they basically take like the nearest neighbors approach. They basically they just have one image of a shoe, one image of sunglasses, and then they test it on the rest of them. So it's just basically saying like,
yeah,
which one's it closer to? Okay.
It's saying sunglasses, and it have a shoe and sunglass.
Yeah. So
it's like, which one is it closer to? Yeah. Or maybe there's a bit of design in here that makes it obviously better. And then the second experiment is when you are increasing the number of training examples you have from 2 to, I think that's 20. What they show is that when you have more training examples, the methods don't perform. The increase in the performance of the methods isn't as much. But the main point that they say is that that the author says is that it's not that much, but within a 95% confidence interval, which is like a statistics test, it's better. So he's saying like, even though when you have more training examples, it's not that much better, it's still better statistically than not using those training examples. But like, yeah, the increase in performance is really small, in my opinion, if you look. So these are like, this is the baseline, this does better, but it's what, by like 2%. Here it's 0.7%. Here it does better. Anyway, so the whole idea behind this paper, the point that the author is making, is that when you have multiple tasks that you want to learn in series, that the experiments, what they're trying to show is that it is better, you'll get better performance using this lifelong learning context. So it's really just a proof of concept for the first time this idea was introduced, which is in these experiments, we're showing that taking into account past data, because we know that it's related, there's similar structure in the tasks, makes it better.
They're still just learning the final one, right? They're not learning all the previous ones.
Well, and yeah,
Like they made the point that you need to learn F shoe, F hat, and F whatever, and it's F sunglasses, but the results are just learning F shoe with the rest of the data.
Yeah. But why do you say that?
Because I thought when I was reading the paper from the introduction, I thought that they would show a method to learn them all in sequence.
Yeah.
But they just learned the last one. It's more like a data augmentation strategy.
Yeah, I would say that. But I think the idea is that you could apply, because it's the nth one, you could apply it, you just apply it in series. Like you would apply the method in series.
Yeah, but you learn different methods.
Yeah.
Different models.
I was actually kind of hoping what they would do is have a method where you learn a model and then you can just retrain it on the new data to improve it.
Yeah.
But I don't think I don't even know if that probably doesn't exist. There probably is, there's definitely papers that have it now, but I thought that would be cool.
That has a problem called catastrophic forgetting.
Oh, yeah. That's what that in modern continual learning papers, you always see catastrophic forgetting.
Which came out, the fifth version that came out just before this one.
Oh, really?
Explaining what it was. And how it broke apart.
Because I think the neural network one, the first neural network one, surely it matters a lot which way you train it. Because if you did all the examples from F1 first, and then F2 and then F3, and then you get quite a different outcome, I imagine.
Yeah.
And if you, when you add F2 and if you shuffle it, like, you know, reinitialize your network and shuffle it with both of the first two classes, then the first three, and then, yeah.
I do think that also I think that the paper is really good, but also you need to put it into context that this was written in 1995. So they were probably struggling with things that now you don't even think about, like how large your neural network can be. Like, because now you would say like learning with hints is like, well, obviously you do like a multi-classification problem, but you need a lot of capacity to learn 100 classes. You need a lot of capacity. Whereas to learn 2 classes, you don't need that much capacity.
Yeah, like what was I going to say? They do the classic example of learning with hints that I've seen is when you want to classify multiple objects in the same image and you don't know how many objects there are, because then you can't have you basically have to have more numbers outputted by your model than the number of objects there. And usually I think it's like, anyway, I had to do this once for a class, but that's an example of learning with hints, which is you want to classify multiple objects in the same image and you don't know how many are going to be there or what they're going to be. And they use that a lot in automated driving now, like how many trees are there, where are they, that kind of stuff.
So how does modern continual learning build on top of things like this? And which was discarded? I'm not as familiar.
Yeah. I mean, I'm not actually, I just chose, I looked, the way I found this paper is I looked at modern methods, but only at the references to see which paper was referenced a lot. So I actually don't know what modern like continual learning looks like. I just know, like Dwayne said, there's a lot of catastrophic forgetting in the abstracts of these papers. So yeah. Cool. Maybe as a discussion point, if anyone has any ideas, is like, how would you use gradients in order to improve your guess? So the idea is that you take into account the model output, f of x, but you also take into account the gradient around that point when you're trying to figure out whether it's actually that point. The only thing I
was going to say, that almost assumes that you're looking at a computer and you haven't trained to convergence. And so the network's only half trained and it's sort of saying for this point, like go that direction. And getting information from that.
Yeah, maybe they use like Euler's method to see if you made like a small gradient step, whether it would change the result of the prediction or something. Yeah, I don't know.
I don't know. I also didn't really.
Yeah.
Yeah, no. What I understood is that they pre-train the gradient network. So the one that estimates the gradient is trained before you want to do your task. And then the classification one takes as input the result of the previous network plus the x plus the function. And somehow that helps.
Yeah.
And there's this tangent prop, which I had never heard of.
Yeah, I haven't heard it either.
But they do use the distance as they here as graph.
Yeah, the distance function. And it's an approximation of bets. Yeah, I guess we have to read about what the tangent prop algorithm is to understand what they're doing. It's funny because the author states that like this is also a paper he published, and like this is a method that he used there. Cool. Does anyone have any other questions or things they want to talk about the paper?
I thought in the problem formulation, when you were talking before about the, illness and another example that happened, and that was the US military trained a whole lot of images to try and detect tanks in the battlefield. You could camouflage them, you could hide them. We ran around took all these photos. It was a great success, like 99% accurate. If you're taking all photos of the tanks on days where there was a blue sky and all the others on cloudy, like it's a classic. I was thinking if one of the earlier tasks that you're doing was say on trees, so it's not directly, you're not kind of species as something like that, not directly task. You do a tank task. You might, the confounding effect of blue sky versus not blue sky might get averaged out a little. So you might be able to get, and I never thought that semi-supervised learning can reduce confounding factors like blue sky. Until you described it just before. I think there's no way to know how much it's doing that.
Yeah. And who knows, maybe it would be better on the previous task if you did that. You retrain on the new data set.
Oh, yeah.
Remember I can't remember what paper it was, but they addressed that issue with the regularization technique. I think they showed this computer vision network that was supposed to identify, I think, dogs and wolves.
Yeah.
And when they saw the attention, they saw that it was only classifying wolves when there was snow in the background.
Yeah.
Otherwise, it wouldn't be able to classify. And there was some regularization there.
I remember seeing those images. Can't remember what they
Yeah, could be. We'll need to dig it up. Also, I don't know how common this task is nowadays. This task of like learning a new concept based on our previous
No,
data.
I don't think it's very common outside of research.
Because in continued learning nowadays, it's mostly around you get new data all the time, and you want to continue training your model, and then you have your catastrophic forgetting that. It's like, or your previous data it doesn't work anymore. You have a drop in accuracy, but
there is something like object discovery in object detection or in instance segmentation, where they take already known objects from, I don't know, and then they try to learn in a semi-supervised and unsupervised manner the new objects that are very tiny, but in hundreds of big objects with normal process.
Yeah, maybe I'll look for a paper on it because I'm actually really, I was thinking more like, at any time we'll often like get a new batch of data from our clients, and it's like that we create a new data set and train our models, but like, what if you could just use that data? Make life so much easier. Yeah. Cool. Okay, I'm gonna stop recording. Thanks everyone for attending online.
any questions online?
I checked. There's no questions. Does anyone have any questions online?
Yeah. So I looked at something the other day, which is when continual learning is used.
Well, anyway, thank you everyone for attending. And we're going to be doing in-person paper club once a month, but we'll continue to do virtual the other 3 weeks.
Yeah.
Enjoy.